Okay, I've started recording. Okay, let us now quickly go to the start. So we sort of left at a very crucial juncture, I would say, last week. Last week it was, that is last class, and it was just one more slide that we needed to cover to complete the proof of convergence for perceptron algorithm. Now, I deliberately did not go into that because, yeah, there are some things that we need to basically discuss in a bit depth in that slide. So let us come to that. So what have we seen till now? So about that proof of convergence for the perceptron learning algorithm. Now, what are we trying to prove? That, okay, the perceptron, let me see, go to that algorithm. So yeah, so the perceptron learning algorithm, it says that, okay, it says that, what is happening? It says that you actually do this update or perform this update, which is new W is old W plus Y times X, if only it is XK is misclassified. So it the algorithm stops when all the examples are classified correctly. That is, all the training examples are classified correctly. So that means K has, the proof of convergence, the idea or intuition behind proof of convergence should be to show that K has a finite value, because otherwise, if it is not convergent, then K will go till infinity. So that is the idea behind, or that is where we want to reach. So let us go to where we were in observation 1. So we found two observations. One is that, okay, we were talking about this W. Again, I will go to the slide mode. Just this old things I'm going here. Okay, so the observation 1 is that before observation 1, this W star is the normal to the maximum margin linear separator. That is kind of the ideal W star that we want to reach. And W dash is your basically the updated W from a previous W. So that is after the updated step. So we have seen that W prime times W star is increasing by at least gamma. What is gamma? Gamma is the margin of separation, the minimum distance between any data point and the hyperplane. So that we have already discussed. So I'm going a little fast here. So this is observation 1, and we want that our W in the perceptron algorithm in each step getting closer and closer to this W star, and that means that the inner product between W and W star should increase with each update. And that's what we are seeing, that for both misclassification for negative examples or misclassifications for positive examples, we see that the W prime increases with each other. Basically, W prime star, W prime transpose W star is increasing in each update. Okay, now if we go to the observation 2, so observation 2 says that yes, the length is increasing, but it is increasing in a controlled way. So that way it will ultimately go and stop with when its length is equal to W star, something like that, the idea. So it is increasing, but it increasing in a controlled way. So ultimately it will converge. So let us see. Let us try to club these two observations. So observation 1 implies this. What does this mean? That with each update, at least this inner product increases by gamma. So if okay, so yeah, say after k iterations, W is denoted by WK. So I'm starting with W is equal to 0, and then after k iterations, I'm denoting this W dash as WK. So WK transpose W star is at least k gamma, because every time it has increased by at least gamma. And observation 2 implies that this is this length of WK, that is the square of the length of it, is less than k, because the initial value of W is 0. Why? Let us go here, because this was the scenario. So it is, if the initial W is 0, then every time it is at least less than 1. So after k times, it is less than total k, less than equal to total k. So these two observations, I hope it is clear basically these two statements rather, this one and this one, from observation 1 and 2. So observation 1 tells that every time this update happens, the W dashed, which we are now denoting as WK after k iterations. So each new W inner producted with W star, that inner product at least increases by gamma. So k, after k iterations, it is k gamma. And observation 2 tells that, okay, it is, after every update, the WK's length is at max 1 greater than the previous one. So as the initial W was 0, the length was 0. So after k iterations, it is less than equal to k. Now we have to apply the Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality, you know from linear algebra. So this is between WK and W star. So yes, so that is the inner product, not inner product, the product of the norm of the two vectors is greater than equal to the inner product of the two vectors. So that is this, but W star is equal to 1. So that's an assumption, or it is true, because W star is just a direction. So you can very well take a unit norm or unit length vector to denote the direction. That does not change the orientation of the hyperplane, right? So this is one. Basically from here to here, what we get is WK, or norm of WK, greater than equal to this, right? And this we have seen greater than equal to k gamma. So this is by observation 1. Now you take the square of both the sides. So basically square of this and this. So k square gamma square is less than equal to this norm square. And we have seen that this norm square is less than equal to k from observation 2. So now if you just look at this and this, then if you try to just cancel one k, then k less than equal to 1 over gamma square, right? So k is finite because gamma is also finite, right? So we mean that when, or we see that when k stops, or k will be at max this. So k will, and when will k stop? When every example will be correctly classified. So at max, this much value of k is there. But if you remember, I said about the theorem that it is beta square. Sorry, yeah, it's, let me go to this. Yeah, it is. Oh, okay. Yeah, so it is beta square over gamma square, but we have seen that it is less than 1 over gamma square because beta we have assumed 1. So that is a more, oh, okay. It's just this. Okay, this. Yeah, so where was it? Yeah, so this was it, but I said that I can also provide you with a proof which is more general, which has this observation, or which has this assumption nullified. So this one basically. So this was the beta is equal to 1. So I mean, that if that is not, I shall provide you. I forgot to give upload it to Piazza. That resource is there. I shall provide it. So just before I stop for questions, I'll just show you one more slide and then stop. So this is basically two class of examples. One is this red class, which is positive class, and this is the negative class or zero class, the green ones. If they are, say, distributed in this manner, that there is no basically linear separator, because you see no linear separator can separate these two sets. So in that case, if you employ perceptron algorithm, it just does not converge. So that's what we have tried to show here with this small animation. So the notation of this color of the arrows, they are same as the one that we discussed last week or last class, when we visually tried to show that it converges, at least for a simple, say, linear, a simple case where very few positive and negative class data were there, training data were there, which are linearly separable. So same. So yeah, it's just an animation that I tried to show. So before I go to the next part, if there is any question, I'll stop here and you can raise your hand. Yeah. Purimal Shatra. Yeah, I have asked you to unmute. Yes.
Sir, what happens if initial W is not 0?
No, yeah. Initial W, yeah, that is one assumption. Yeah, I mean, the algorithm says that. I have not. Yeah, I mean, you can always make the initial W 0, but yeah, I don't have a very good answer because I don't really know. We have to see. Maybe.
Okay. No problem.
Yeah. 0. Where are you using that W is equal to 0? Yeah, that's the way basically. So this, so everywhere else this W will come. Yeah, we have to think a little. I mean, just you need to see where are we using that W is 0. So I think it is only here we are using the W is 0. So only a W term will be there in here. So it will be probably that W's the initial W, if I call it this square plus K, then will that change anything? I think it will not change anything. It will come here, then W square plus K, then you just divide it by, so just one constant term will be there, if I am not too wrong, because this will be W0 square plus K, so you divide it by K. Yeah, there will be 1K. Yeah, I think there will be some constant term either here or there. So that much math you can do. Yeah, any other questions? Okay, if not, Purimal, if you can unraise your hand, I'll go ahead then. Yeah, let me go to this. Yeah, so this is kind of a filler sort of slide. I mean, that we will need later, but this connects to something that we talked last lecture or last topic, that in perceptron we are using a thresholding function. So threshold does not, I mean, a threshold function, since it is discontinuous in terms of its computing its gradient, so we rather will not be able to use any gradient descent sort of an algorithm if we use this thresholding function. Where are we thresholding? So W transpose X plus B, if it is less than 0, then we are telling that it belongs to the output is that it is negative class, and if it is W transpose X plus B is greater than 0, then we are saying that the input belongs to the positive class. So that is where the threshold function we are using. That is the I mean, you are thresholding depending on what is the whether W transpose X plus B is greater than or equal to 0 or less than 0. So we have also discussed that we can use a sigmoid function, which is a softened version of thresholding. So it's not just directly just a straight line going from 0 to 1 at one single value 0, but it slowly goes to 0 to 1. So similarly, there are many other activation functions that we can use, which are equally useful. There are some disadvantages that you will, I mean, that basically depends on the nature of the data, etc. But one very simple one is linear activation function. So linear activation functions, though it does not introduce the requisite non-linearity sometimes. So if the data is not linearly separable, then sometimes this basically will not work. So this is one, but this does not add much value, because you need to squeeze the values between 0 and 1, sometimes -1 and 1 to basically make your decisions. So that will come with the sigmoid activation function. We have discussed about this. This is the form of the sigmoid activation functions. The input is a, then what is the output? 1 over 1 plus exponential of minus a. It is bounded between 0, 1. This output is bounded between 0 and 1. So it is either, between 0 and 1. So for a very, pretty much negative, the GA will be 0. And for a, which is pretty much positive, so it will be, GA will be 1 and so on. And it is always positive. This is the derivative of GA with respect to a. So remember these things. We will require this when we discuss in more detail the backpropagation algorithm. Similarly, this is the tan H activation function. It is very similar, but yeah, this form, what it makes is that it is between -1 and 1. So it can reach -1 instead of 0 at the very highly negative values of a. GA will be -1 for tan H and GA will be 0 for sigmoid. The derivative of it is this 1 minus G square A, can be positive and negative. This is -1 and +1. There is one very popular one which got its popularity around 2012. I think it was in with the very first, not the very first, but with the paper that rejuvenated, I would say, coordinates. That is the AlexNet. They use ReLU. I have to just check. But we have that in subsequent lectures. So it is bounded below by 0, but not upper bounded. So it's basically is linear. Just this part of the linear is taken, but these for all the negative activations. That is, I'm not using the term activations at this moment. We will come to that. For negative value of a, the GA will be 0. So that is called ReLU. It is rectified linear unit basically. So this is linear, and this has some rectification in this negative part. So that's sort of the full form. And G. So this is, the derivative. It's very easy to see that this is 0 in this part and this is 1 in this part, and there the concept of subgradients are there, which I am not going. You can take any gradient which is between 0 and 1. Okay. Okay, so this is again a kind of a very brief treatise on it, but let us go back or come back to what we were discussing. So it is that, okay, we have seen that we can do some sort of linear separator or learn a linear separator. By learning, we mean that the W, that the weights, that is the hyperplane, or the W that dictates the hyperplane, that specifies the hyperplane, that we can learn in perceptron algorithm, but the data has to be linear. Now let us see if we can go with more layers and what are the advantages that we can get. So what have we seen earlier? We have seen that we had some X's. Basically, I don't have to draw, here it is. So these are just d-dimensional input. So you have an X which is represented as a vector of dimension d. You are combining them with W's. So DWs are there. So W1, W2, WD, and you are taking a sum of it. So basically of these forms of it. Just try to write it. So it is basically X1, W1 plus X2, W2, and so on. And then says, this at the end, this B is there. And we can also think it as W0. And X0 is 1. So, but we'll come to, you have seen it in single layer network. Let's not call it a neural network at this point. So what does this single layer mean and what we will have in multi-layer? Let us see. Single layer basically means that you have one, you have one set of these W's and then directly you are getting the output. So after you linearly combine them, you pass it through some activation function. In our case, or in perceptron, the activation function was what? Threshold, right? But we have seen in just the previous slide that activation function can be anything. I mean, not anything. There can be many choices of activation function, but the basic philosophy is that you combine linearly the inputs, and then you pass it through some activation functions. You get the output that will directly give you the class decision. Now, this is, I mean, we will see that in multi-layer neural network, we can actually pass this output or pass the output after this activation. That is what we called as the activation. This was, you remember, pre-activation, and this is activation. So these activations also can be given as input to another such unit where you have you will linearly combine these activations and you will basically then pass it through again activation function and so on. When we will discuss it next slide, we will see. The thing is that, so that, I mean, now you see that, I mean, just for one single layer, we are taking so much space to denote it. So just so that the notation is compact, because we will further process these activation functions with different layers, we are just compacting the notation a bit. So basically this whole red square, we are just clubbing it inside this. So if I say, if I give such a figure, it means that you are getting y as g of this w transpose x plus b, this whole thing. So previously this a was w transpose x plus b, and then this it was passed through g. Just this is notational change, nothing is changing in inside. Okay, I see one raised hand. I will stop and ask Anupam to unmute. Yes, Anupam.
Sir, my question was a little bit general. Sir, why is it important for each, for example, sir, multi-layer neural network, sir, why is it important for each neural network to have, each node to have a bias? Can we not add a bias at the end, like one final bias towards the end?
Anything you can do. That's just this will put you to a separate hypothesis space. Okay, so you remember that we discussed about the space of hypothesis functions. So you can use actually in many other in some convoluted architectures, no bias is used, even no bias.
Okay.
Yeah. So that just will put you in a separate hypothesis space. Okay.
Okay, sir. Thank you, sir.
Yeah. Okay. Let us go ahead with this one. Okay. I see a few raised hands. Okay. Let me ask Kaushik to. Yeah, I have. Yeah.
Just one basic question, that instead of using the activation function at each layer, if we use it at the last, at the final layer, how do you see the difference?
Yes. Again, I mean, I think the most safe answer would be to say what I said to Anupam, that you can always do that. The thing is that there can be many perspectives. I'm just giving my opinion. One is that you suppose you have like 10 layers, but you are not using any activation function in between. So what you are doing in these 10 layers are just linearly changing the data. So basically you are doing linear combinations. So I mean, if the data is too complicated, that linear separator will not basically be able to separate the classes, then I mean, you are just not giving a good chance to the network to basically deal with the nonlinearity. So at the end, you are just giving one nonlinearity. So it is better that if you give more chance to the network by giving more options of imparting nonlinearity. So again, it's a little I would say vague answer, but that's what I think will be the problem. If it is very simple data, you can always do it without, I mean, with less number of activations. So in summary, what I want to tell is, yeah, I mean, you can try and it will just put you in different hypothesis space. For simple data, it should work. For not so simple data or complex data, you are not probably giving a good chance to the network to learn the nonlinearity. And I think another answer or another trend is basically nowadays, mostly this came from the transformer architectures. People are using less activations. So some layers are without activations and so on. I have to go a little deep into this when we will discuss transformer, but that has been a trend for last, say, 2 years. So you can, I think there is a very good paper which I am expecting people to, which I have given as the paper presentation. It is called a ConvNet for 2020s, which came in just this January. It's from FAIR, Facebook AI Research, and then Berkeley, some students, faculties are there. They actually showed that in that paper, if you take some little tricks from transformer and apply it to ConvNets, it does as good as the ConvNets, if not better. It does as good as the transformer, if not better. And one of the tricks was that. Does that sort of answer your question?
Yes, sir.
Okay.
And would it be okay to, or what do you think about this? Like, there is also a school of thought that, instead of adding the non-linearity or the activation function at each layer, if we do a normalization, across all the nodes, then say min-max normalization or a standard normalization, then also maybe we can get similar results.
Yeah, probably. I mean, probably batch normalization tries to do some such things. If you are pointing to that, I'm not totally sure. But batch normalization comes after the activation function. So that is there. Yeah, I mean, many things can be done. I mean, it's just a combination of different things. There are different normalizations that has come in recent times, like group normalization, layer normalization, etc. Maybe you can try to look into this.
Sure.
I'm not aware of all of these things. Yeah.
Thank you.
Yeah. Rishabh, I will just wait for your questions later because we need to go in this, and you can always come to the office hours for such questions. Okay, so multi-layer neural network, let us go. So this is, so multi-layer neural, this is basically the notation that I have given. So this is, this is, I mean, the same inputs, x1 to xd, hidden layers. So this is the, I mean, though I am telling multi-layer neural network, here just one hidden layer, that is one additional layer I am adding. So previously it was this and this directly, but now here you have this something called the hidden layer. So this is the input layer, this is the output layer, and everything in between will be hidden layer. So there can be 1, 2, 3, 4, many hidden layers. Let us now just try to familiarize ourselves with this hidden layer, I mean one hidden layer, and then we will go. So hidden layer, the idea is that it extracts better representation. Basically, it hierarchically combines the representations that is learned in each layer. And that is kind of supposed to give more or impart more nonlinearity, more learning capability to model the complexity of the data. So let us see at least what the output will be, and then we will go on how to learn the parameters there. So output layer does the classification. So let us move ahead. Okay, so I'm just taking the first node in this hidden layer, the first hidden layer. So it can have many nodes. It can have 1 node, 2 node, many nodes. So let us see the first node. What is the input output relation there? So again, very simple. If you look at this picture, it is very similar to what we have seen in the perceptron thing. Just that this thresholding function is just replaced with a more general activation function. So there it was x1w1 plus x2w2 plus xdwd plus b, right? Now you have 1, 1, 1, 2. Why do we need that? Because from this to this, okay, let me go to the previous slide. From this to this is say some w1. From again this x2 to this one is some w2. But from the same x1, there is a connecting link between this node or even this node or even there is some node here, that node. So we have to like separate or differentiate between those W's. So how, I mean, for the purpose of the next slide, that is when we are discussing this, what are the W's that we are requiring? We need all the W's that are converging to this GA, right? So this, and so on, right? So this, and so on, right? So let us see. So I mean, again, just I mean, probably it will be easier from this slide. So this to this, that is 1 to 1. This is 2 to 1. This is D to 1, right? Let us see what we have here. Oh, yeah. So this basically means that your pre-activation function, or what is the result after linearly combining these X's and W's, will be, yeah, let's try to write it. It will be your W. Okay, I'm not giving. Okay, yeah. Let's see. W. This is 1 1. What is 1 1? I'll tell. X1 plus W1 2 X2. So the notation is that this is from yeah, and this is 2. This is from, this is 2. So from X1 to this or the node 1 of the input to node 1 of the hidden layer, node 2 of input to node 2 of the hidden layer. So node 2 to node 1, node 1 to node 1, node 3 to node 1, and so on, right? And then ultimately this B is there, of course. So this is how the notation, this is again, I'm just telling about the notation. So 1, I to 1. So ith input to the first hidden output or hidden node. So this now, then we can write it again very similarly as the matrix vector or the vector products. So this W1 1, this basically this W1 1 1 2 1D etc. They are like collected in a row vector, and we are denoting it as this bold lowercase w1, and on top there is this superscript which tells which layer it is. So in general it is Wij. So this is the lth layer in lth hidden layer from J to I. So that is sort of, I mean, try to be familiar with this notation. I'm trying to be as lucid as possible, but you need to, of course, sit down with the slides if possible before the class. That I will again always encourage. So this is the form that A1X. A1X is called the pre-activation, right? It goes to the activation function and then it gives the activation, hidden layer activation. So H1 is hidden layer activation. So A1X is, this one is tells that denotes that it is the first node of the first node of the hidden layer. And which hidden layer? The first hidden layer. So generally superscript, at least for the purpose of this lecture, this course, superscript means generally the layer number, and these will be the node number, right? And for W's, it has two connotations. One is like I, that is from where to where, right? So hopefully this is clear. Just again, as I said, you need to just sit down a little bit. Okay, so you get A1 as your what is called pre-activation. I think it is written. Oh, okay. Ultimately it is written probably after the third slide, and this is called the activation. Okay. Similarly, if you go to the next node in the same hidden layer, that is the first hidden layer, you have I to 2, right? So 1 to 2, 2 to 2, and so on. So I to 2, then X1, so, or Xi, so W21 X1, W22 X2, and so on. It's very similar. So A2 is the pre-activation at this node, and H2 is the activation at the same node. G is denoted, I mean, the activation function is denoted by G. So G can be your sigmoid, tanh, ReLU, linear, etc. Right? Similarly, the mth node. So I'm not going into this. Now we can basically club all these things. That is this A1 1x, A2 1x, and A2 1x. And also these things also we can combine in a separate vector, because these are scalars, right? This is a scalar, this is a scalar, this is a scalar, because this is just inner product. And then it goes through the activation function. So all these are scalar. Okay. So we can combine, let us combine the A1, A2 to AM first. So A1, A2 to AM, we are just writing the right hand side, and you can very well write it as a matrix vector product. So this is W1x times B1. This is W2x times B2, which is A1, A2, etc. respectively. So this is, I'm denoting it as now this is a vector, right? I mean, this whole thing. So this is just lowercase, the notation that we earlier introduced, right? The lowercase a with this is the layer number as superscript, and this is the input. And this is just W is a matrix, because now these are all, this is a row vector, this is a row vector, this is a row vector, right? And this is again a column vector, this B, all these B's, okay, all these B's, and this X1. So you just again, I think this lecture is all about just carefully noting the notations. Okay, just very small space here. Hopefully from next week I'll go and take the class from office. Okay, so this is column vector, matrix, column vector, and vector. So A is WB X1. Now you can imagine that what will be the next step. The next step will be hidden layer activation. So the hidden layer activation, we are clubbing them, right? So H1, all these hidden layers, basically H1, H2 to HM, you are just clubbing, and you are denoting it in this way. So basically, just one thing to note here, important thing, this G is what's element wise. I mean, it is not just G times A or anything. This just means that your first element of A1 that goes through the, say, sigmoid. Sigmoid is the, say, the activation. G is sigmoid. Second element of A1 goes through the same G and gives you this H2. All these you are just collecting. Okay. Now we are going to the last, that is the output layer. So we have told that we will, for this lecture, not for this lecture, I mean, first we will see what is the case for one hidden layer. So this is one hidden layer, and this is the output layer. So we have got this H1, H2 to HM. Now you similarly combine with this W11, W12, but for the second, basically not second, but the last layer, which is the output layer, which is the layer, so layer number, this 2, this superscript. So because these were all 1, right? So you have to have some something else which is 2. Now it happens to be the case that here the second layer is also the output layer. It can be that second layer is the second hidden layer, third layer is the third hidden layer, then fourth is the output. That can also be true. But here, since we are just introducing the multi-layer neural network with one hidden layer, we are basically doing this. So output layer pre-activation. So we have seen how to compute the pre-activation. It is just linear combination. So these H1, H2, HM, this will form the input to this output layer. So that's why here it is, and this is W1 to B1, and output layer activation. This has a special name O. Just I mean, there is no other reason than one thing, that is generally this output layer activation is different from all the input. The hidden layer activations. Generally, the hidden layer activations are the sigmoid, tanh, etc. And this is something called softmax. So let us go into that. So O can have many options. So sigmoid, tan, H, relu. That can also be true. O can have these, can very well be these. But one special is this softmax function, right? So the softmax function, what is this? Let us try to see this, and then we will stop for a few questions. So multi-layer neural network, and then what softmax functions allows you is to get different or multiple output nodes in the output layer. So it may be that you are actually going for a classification problem where you have, say, multiple classes, not just two class, positive and negative. There only one node would suffice. Just it will give a value between 0 and 1, and that you can model as your probability to belong to one of the classes. But if it has like 10 classes, then you probably need 10 nodes, which the first node, 10 nodes in the output layer, where the first or the value at the first node will give you, say, the probability of belonging the input to the probability of the input to belong to the first class. The second node will give you the probability of the second probability of the input to belong to the same input to belong to the second class. So basically the sum should be 1, and since it is probability, all these values will be between 0 and 1. And that is actually what is achieved by the softmax function. And how it is very simple to do. How can you do this? So suppose your output activation is O1H2, which you can also call basically. So yeah, this is I mean, I'm just not using the layer superscript here. It will be just 2. But 1 means the node number. So basically you can also tell this is H21, this is H22, and so on. But which is same as this, which is same as this. So what you are doing is you are exponentiating each component of the output activation vector. What is output activation vector? Just these things. Okay. So since this is output, instead of H2, 1, H2, 2, I am just calling it Y1, Y2, etc. So because it's like we are trying to learn a Y is equal to Fx, of course, by parameterized by the parameters thetas. Thetas are just the collections of W's. So you exponentiate each of these, that is W, Y1, Y2, IC, and element wise divide by the sum of these exponentials. That is what exactly it is written. Exponentiate these and sum of them you are dividing. Now, if you see, I mean, notice carefully, these are all between 0 and 1, positive, and the sum is 1. So that way, you can take it, I mean, what we told earlier, that as the probabilities. Now, this is probability that X belongs to class 1, X belongs to class 2, and class. That's what I was saying. So we can aim to maximize the probability corresponding to the correct class for any example X. That way we can try to, that will be our objective. That okay, if our network can do that, then we are done. For whatever W's, set of W's that can do, we will take it as our learned weights. So what our objective is, maximize YC. And you have seen it that logarithmic is a monotonically increasing function. So whatever maximizes YC, that also maximizes log of YC. So the objective functions, changing these objective functions to this monotonically increasing function does not change anything. Now max of a thing is basically same as minimizing the negative of it. So that is what we will try to do. And this can be equivalently expressed as this, known as the cross entropy loss. So this is a cross entropy, in literature, it is called cross entropy loss. This comes from the information theory literature. We'll not go into that, but it is very easy, like why it is called cross entropy. I'm not going into that. So let me actually stop for, say, one question at this point. If you have, otherwise at least I should try to complete the forward pass. Yeah, if you have any questions, please raise your hand. I'm seeing Kaushik's hand raised. I'm asking you to unmute. Was there any question?
Sorry, I did not lower my hand.
Oh,
Sorry.
okay. Okay. Yeah, then Deepak, can you ask quickly the question? Deepak, I see your raised hand. I think asked to unmute. Yeah.
Sir, slide number 26.
26.
So,
This one. Oh,
sir,
yeah. Mhm.
sir, if a layer have n nodes, it means then we are assuming that we are exploring the n hypothesis space.
No. This is just one hypothesis where all the networks will have one hidden unit, and that hidden unit, that particular hidden unit will have n nodes. Okay. So
Sir,
this,
but by changing,
yeah,
but
then,
by changing
then the hypothesis function changes. If you add or subtract some nodes in that hidden layer, then the hypothesis function changes, right?
Yes, sir. Then what can I imagine about if n nodes are at layer, then what can I imagine that what they are performing? They are doing this different. They are taking the different function.
Yes, they are just taking different function. They are just taking different functions. So hypothesis and function, you can take it the same thing.
Okay, sir.
Okay. Okay, let us then go ahead with the forward pass, because I think we will not have the time to discuss backward pass. So now forward pass in a nutshell, this basically what I am trying to show here is that now we can go ahead with multiple hidden layers. So X was the input. We can very well think that X is the 0th hidden layer. It's not hidden. It is basically the input, but for the purpose of the discussion, we can think it as H0 similarly. Then what we have seen is W1, B1 to give the A1s, then activation function, through activation function it goes and it gives the H1. From H1, we get directly the basically A2, but earlier it was going directly to this O, right? Now, what we can think that, okay, whatever this H1 we are getting, it is very much similar looking as H0. By similar looking, I mean that it is also another vector. This was a vector, this is a vector. So whatever operations you did with this, you can do with H1 also. So you are passing it through, okay, so this is also called a linear layer because it's just linear operation. So W transpose X times B, which are all linear operations. So it is W2 transpose H1 plus B here. Then you pass it through. So you get the pre-activation of the second hidden layer. And then you pass it through the activation function. So you get the activation of the second hidden layer and so on until there are L layers. And after that, the Lth layer is basically, you can think as the output. This is your Y, which is equal to fx theta. Now, x is the input and theta is the collection of all learnable parameters, that is all W and B. Now, as we have seen in the last slide, that we are after, or our objective is to get these thetas, which will, that is the collection of all W's and B's, so that the probability for each of these, so yeah, so you can aim to maximize the probability for the correct class of any example X. So that is our aim, and for that we have to do the gradient descent, because that is I mean, why we are using different sorts of activation functions, not the threshold function. I mean, you can come up with any other method which will just give you, which will just suffice to reach to your objective, which was to get the correct classes probability the highest, right, for all the examples. But we are, since we are in the gradient, we are trying to study how to do it via gradient descent. We will assume, I mean, those differentiable activation functions. So yeah, this is just the hidden layer pre-activation, the same thing. just for a multi layered neural network. It is WLH L minus 1 BL, just it generalizes more. So this is a, suppose this is HL minus 1, this is this WL and BL. See, this is 1, this is 2, 2, and you are getting 2. So this is L is suppose 2, then it is W2 H1 plus B2 and so on, right? These are all notations mostly. Now hidden layer activation, note the difference. Here it is still L, here it is still L minus 1. So we are getting these HLs till this I mean these where are these? Yeah, this one, and so on. So this is still L minus 1. You are passing it through your G activation function. But for Lth layer, that is the output layer, you are passing it through these output activation functions, which very well you can think as the output activation, which is very well you can think at as the softmax for classification. And mostly that is taken, which is equal to fx theta. So this is forward pass in nutshell. So when you pass an input x through this whole network, the f that you get is given by these set of equations. For all the L layers, you get AL, but of course you have to do it sequentially. So this AL you get, suppose for A1, that is A1 you get, then you get H1 using this, then you get A2, H2, A3, H3, and so on. And for the L minus 1th layer, you get the, for the Lth layer, you get a capital L, and then H capital L you get via this, not this. Okay, this is the forward pass. So you are passing X and your information gets passed through this. So there must be some backward pass, and why we will need that, let me just try to introduce to you. So back propagation. Again, I mean, that was the goal objective, that we want to get these thetas which will maximize the probabilities. And J, I mean, this is the fx theta, and what is J? This is the cost function or the objective function, which is one very simple, was this negative log of YC, right? So you need to get all those Y's, Y1, Y2, etc. And then you also need to know what is the true class of the example, because otherwise you don't know which of these Y's you should take. So the cost function is a function of not only fx theta, but you need to know the true class of the example. So in case of regression, it was, say, the true value of the output, and this was your predicted output. So in general, your cost function or the objective, again, objective and cost function, they will be basically interchangeably used. Objective you maximize, cost function you minimize. So there is a very famous quote by, I think, Sergey Levin in one of his reinforcement learning course. So quickly I'll tell. So I think he said, he's a Russian. So he said that, okay, Russian scientists, I mean, they coined this term objective function. They want to maximize something. And the American scientists, they use this cost function. So he said probably Russian scientists are more happy. They want to maximize the things, objective, not the minimization of cost function, looking everything as cost. So yeah, again, very briefly that I told. So, but yeah, I mean, again, it is just opposite. I mean, objective and cost function just negative of each other. So maximizing objective and minimizing cost function is very same. Okay, now for gradient descent, we have seen this earlier, that we need del J, del theta, right? Or del J, del W here. Now this is for all Ij, all L. If you get that, then only for all these Ij's and all these L's, you will get the new W's, which will be Ij, L previously, then basically the minus step size, this thing del J, so this is step size, del J, del W, Ij, L, right? That you will get. So back propagation consists, but yeah, so the way to get this is back propagation. So we have seen forward propagation to move in this way. So X, then you compute H, A, then H, then next A, then next H, and so on. here we will see how to compute these gradients, because we need, why do we need gradient? We need to perform this line. To compute these gradients, we have to pass the information in this way. So from f to these derivatives and so on. I'm not telling what exactly, but we will consider it next week. Rather, tomorrow is the class test. So backpropagation consists of intelligent use of the chain rule of differentiation for computation of these gradients. We will see how just simple chain rule of differentiation gives us backpropagation. But yeah, I will not start backpropagation today, but what I will, probably request you, urge you, please go through these slides, because backpropagation is not a thing that you will probably learn in a class. It is not possible, but I have tried to make these slides as comprehensive as possible. So please go through these slides, and we will discuss it in the next class. Okay, so I see a raised hand. I'm allowing Anupam to ask the question, and then I'll go to the logistics related discussion for tomorrow's test. Yeah.
Sir, my question was basically, sir, why is the non-linearity needed for learning?
This is because you have seen that the data that is not linearly separable, you cannot learn the basically the separating boundary or hyperplane for we using only linear activations. So I think that was the slide. It's gone. This was one visual example.
Okay.
Yeah, so you need to impart the nonlinearity there. Yeah, I
Okay,
see one more question from Rishabh. Yeah, please.
Yeah, sir, I didn't understand one thing. How are the activation functions actually contributing towards classification?
Yeah,
Because,
so this is, you can think of it as you need to, first of all, you need to introduce some nonlinearity. Otherwise, you will not be able to get these nonlinear separations. But if you just think about just the, say, the output layer, they are also for say classification, you need some decision between 0 and 1, right? I mean, either -1 or 1. You have denoted it as say positive plus as 1 and negative plus is 0, or positive plus is 1, negative plus is -1. So that will help to squeeze them from unboundedly increasing. So these are again for mathematical conveniences, which again we don't have scope to go into much detail, but this will keep things mathematically bounded. Okay. If there is not any other questions, let me actually go ahead with your logistics